The assembly constraints, mate, angle, tangent, and insert, allow you to define a range of motion for a component. You can specify a minimum and maximum position, and you can also define a default position. In this case, I'd like to establish a range of motion for this simplified piston assembly. If I move the rod, you can see it is already centered in the cylinder using an axial mate. However, notice the rod is free to slide completely out of the cylinder, and it can also overlap the cylinder at the bottom of the stroke. To eliminate these problems, I'll create a mate constraint between the end of the rod and the bottom of the cylinder, and then I'll add limits to define the range of motion. I'll start constrain and select the faces for the mate. Next, I'll click on the More button to display the limits fields. There are 3 settings: use offset as resting position, maximum, and minimum. I'll enter 100 millimeters and 5 millimeters for the maximum and minimum settings, and then click OK. As I drag the rod, you can see it stops when it reaches the ends of the range I've defined. I'll edit the constraint so I can show you how the resting position works. When I added the limits, the offset field was disabled because there was a range of motion instead of one value. When I select the Use Offset as Resting Position option, the offset field is enabled again. I'll enter 20 millimeters and click OK. As I drag the rod, it still moves within that range of motion, but it snaps back to 20 millimeters when I mouse up. Although you still get the range of motion, it goes to the resting position unless another constraint holds it in place. You can also use just one of the limits. I'll edit the constraint again and deselect maximum. Now I can drag the rod out of the cylinder and it still snaps back. If I try to move it to the bottom, however, it still stops at 5 millimeters. There are 2 important types of motion constraints in Inventor: rotation and rotation translation. Rotation is similar to a belt or gear drive, and rotation translation is similar to a rack and pinion. We'll discuss the rotation constraint in this lesson and the rotation translation constraint in the next one. The rotation constraint is used to replicate the motion of connected gears, pulleys, or any components that have related rotational motion. It's important you understand that there isn't any physical interaction between the components in the assembly. You enter a ratio for the relative rotation when you create the constraint, but it doesn't automatically update if the diameters of the components change. Again, there is no physical interaction. This simply allows you to try and emulate the motion of the mechanism. In this lesson, we'll take a look at how to apply the rotation constraint to a pair of pulleys as well as a pair of gears. At this point, the 2 pulleys are free to rotate independently of each other. To simulate a connection between them, I'll start Constraint and click on the Motion tab. The rotation type is selected by default. The rotation constraint is defined by selecting 2 axes of rotation and specifying the ratio between them. Selecting an axis of rotation can be accomplished several ways. You can select an axis, a work axis, a conical or cylindrical face, an arc, such as the circular edge of this pulley, or a linear edge. In this case, I'll use cylindrical face on the rim of each pulley. By selecting the faces, Inventor can calculate the ratio. Keep in mind, this is not a parametric relationship. If you change the diameter of one or both pulleys, you'll have to update the ratio. Before clicking OK, notice the 2 solutions are forward and reverse. Forward causes the components to rotate in the same direction, like pulleys, and reverse causes the components to rotate in opposite directions, like gears. The default setting is forward, so I won't change it. I'll click OK and the rotation mate is added. I'll quickly check to make sure the constraint is correct. When I turn the handle on the green pulley, the blue pulley rotates more quickly. In the next example, let's take a look at creating a rotation constraint between two gears. The process is not much different than the previous example. I'll select the z-axes of the gears and select the reverse solution. Once the axes are selected, I'll define the gear ratio. This time, I'll enter the number of teeth on each pulley, 29, 16. I'll click OK, and the gear mate is complete. I'll rotate the gears to make sure the direction of rotation is correct. If you have to change the gear ratio, just click on the constraint in the browser. The Edit field shows you entered 2916, so you can just update the number of teeth. Keep in mind this is only a simulation. The gear teeth are not actually interacting and may in fact be overlapping. The rotation translation constraint is used to simulate the linear motion of a rack with the circular rotation of a pinion. It's important you understand that we're simply emulating this motion here. It's not a true physical interaction between components. Here on this assembly, if I move the rack or rotate the pinion, you can see they're both free to move independently from one another. I'll use undo to return them to their original positions, and then add the constraint. First, I'll zoom in so we have a better view of the geometry. Then, I'll click on the constraint icon, switch to the Motion tab, and select the Rotation Translation type. Next, I'll select the pinion shaft and an edge of the rack. Now, I need to specify the distance the rack travels per revolution of the pinion. The easiest way to do this is to use the pitch diameter of the gear. I'll enter pi times 4.95. The default solution is forward, and I usually don't change it. If the pinion rotates in the wrong direction, I can just click on the constraint in the browser and make the distance value negative. I'll click OK, switch to the top view, and then move the rack. You can see the pinion stays in sync with the rack. Keep in mind this is only emulating the motion based on the pinion pitch diameter value I specified in the Property Manager. The gear teeth are not actually interacting and may in fact be overlapping. Also, the rack has a limit mate for its travel distance. If I drag the pinion, notice I can continue to rotate it after the rack stops moving.